is the most basic science. Physics deals with the interaction between matter and energy. Um, it's both an experimental science and it's also a theoretical science. Scientists make observations, they form hypotheses. A hypothesis is an educated guess that a scientist is capable of testing. If you can't prove a hypothesis wrong or test to see if it's wrong, then it's not a valid hypothesis. Once they form these hypotheses, they have to do experiments and collect data. That means they're taking measurements. Okay? Most of this video is going to deal with measurements. They look at the data, they form conclusions, and then if necessary, they will go back, they'll revise their hypothesis, and they'll do more experimentation. It is an ongoing process. No matter how much experimentation we do, we can never prove a theory is absolutely correct under all circumstances. It can take only one experiment to prove a hypothesis wrong. Okay. One of the things we have to understand when we are collecting data is that every measurement has some degree of uncertainty. Let's think, for example, that you want to measure the width of a board and you get out a ruler. The ruler is marked on one side to inches all the way down to a 1/16 of an inch, and on the other side it's marked in centimeters down to the 1/10 of a centimeter or a millimeter. We're going to measure on the centimeter side because science generally uses the metric system. So you measure this board and you get that it is closest to 8.8 centimeters. That's the smallest marking on the ruler. It's also called the precision sometimes. What that tells us is you don't know it exactly to 8.8 because what if it's 8.82 or 8.823? You notice we can keep adding digits, but our measuring device limits how precise we know this. We normally consider the last digit in a measurement to be uncertain. So in this case, if we measure 8.8 centimeters, we generally mean plus or minus 0.1 centimeter. That last digit always has a certain degree of uncertainty in it. We can express that uncertainty as a percentage. A lot of times we do what they call a percent uncertainty. In this case, it would be the amount of the uncertainty divided by the measurement. And then that will give it to you as a fraction. Anytime we want to make it a percent, we multiply by 100. Notice the units cancel out. Centimeters divided by centimeters. And this comes out to be approximately that wavy equal sign, 1%. Okay. Another way that we can talk about uncertainty that we use sometimes in labs is we can write it as a range of values. 8.8 minus 0.1 would be 8.7 centimeters. 8.8 plus 0.1 would be 8.9 centimeters. So we're very confident that we know it. It's between here and here. We feel like we have about a 1% uncertainty. Now, most of the time what science does is we write our measurements, we're using something called significant digits. The significant digits tell us which digits are meaningful. And we don't write measurements with digits that are not meaningful. Let me give you an example. We go back to this measurement right here. Those two digits are meaningful because we actually were capable of measuring to the nearest 10th of a centimeter. That's where our ruler is marked. It would be wrong to write this, because that would imply that we actually measured out to the hundredth place. Well, we didn't measure to the hundredth place. I don't know whether this is 8.81, 8.83, 8.76. I just don't have that degree of precision. Okay. So that would be wrong. If you saw this and somebody wrote this, then you are to assume they actually took this measurement all the way out to the hundredth place. And that could be possible with a different, if they used a micrometer instead of a ruler, they'd be capable of measuring this precisely. Well, in that case, they should write it. Okay. So this is a meaningful zero here. It means something. Okay, so what are the rules for significant digits? These are often called sig figs, significant digits or significant figures. The first rule is all non-zero digits are sig figs. If you are reading a measurement and it doesn't have any zeros in it, then you can feel confident that all of those are significant digits. So 24 kilometers, that would be 2 sig figs. 308 or 382.7, that'd be 4 sig figs. I'll put it in meters. If there's not zeros, it's really easy. If it's written in scientific notation, it's easy. 6.32 times 10 to the 5th seconds. In scientific notation, you look only at the digits on the left, and those will be significant. So this has 3 sig figs. This 10 to the 5th over here doesn't affect the number of significant digits. So if nothing's a zero, it's really easy. Our second rule says all zeros between sig figs are also significant. So for example, if you had the measurement 503 feet. Well, we know the 5 is significant. It's not zero. We know that 3 is significant. So 503 feet has to have 3 sig figs. If you have 1.006 millimeters, again, the zeros in the middle are significant. So, also a pretty easy rule. If the zeros are sandwiched in the middle somewhere between non-zero things, they're going to be significant. All right. All final zeros after the decimal point are sig figs. Notice this is really important. They have to be final zeros and they have to be after the decimal. So for example, if you had the number 12.30, that's a final zero, and it's after the decimal point or to the right of the decimal point. That means that this is significant. So that would be 4 sig figs. Or if you have 0.200, these are after the decimal, they're significant. This 0 in front of the decimal like this is not going to be significant. So this is actually 3 sig figs. Again, if something's in scientific notation, it's always obvious. If somebody writes 7.00 times 10 to the negative 2 millimeters, that is going to be 3 sig figs. Notice I just used SF for sig figs. In scientific notation, it's really going to always be everything you see there. Leading zeros are not sig figs. What's a leading zero? A leading zero means it comes at the beginning of the number. 0.0023. All of those zeros are at the beginning. These are not final zeros. They're after a decimal, but they're leading zeros. That's only 2 sig figs. Anytime zeros are at the beginning, they're not. Final zeros before the decimal are not sig figs. So if you have a number like 2,500 meters, that number only has 2 significant digits. These zeros are final zeros, but there's no decimal. So that's 2 sig figs. If you have 3,000 meters, that's 1 sig fig. The implication here is that's only been measured to the closest thousand. If they want to write that with more significant digits, then the secret to writing with more significant digits when you have something that's nice and round like that is to write it in scientific notation. If I know that I measured all the way to here and I want every single digit to count, then I'm going to need to write that 3.000 times 10 to the third meters. That shows all 4 significant digits. Mathematically, this expression is identical to this expression. Okay, let's carry on. Let's say you've got some measurements and now it's time to do some calculations. Maybe you want to calculate the volume of a prism. Maybe you want to calculate how many miles per hour or meters per second something's traveling, but you need to do some math. How many significant digits should we put in our answers? There's 2 simple rules. First rule is when you add and subtract. When you add or subtract, the result has the same precision, and we can think of precision a lot of the time as the number of decimal places. Although if there's no decimal places, we'll look at those examples too. The same precision as the least precise adding. Now, while we're talking about adding and subtracting, when we add and subtract measurements, they all have to have the same units. We can't add feet and inches and centimeters and meters together. We would have to get all of those in the same units. Let's assume that we have everything in the same units, and we want to look at an example like 7.8 meters, 12.25 meters, 4.3 meters. 3.1, might have one more, 4.31 meters. Now, if I get a calculator and I can easily add this up, let's get a calculator and do that. I've got 7.8 plus 12.25 plus 4.31. Comes out to be 24.36 meters. Now, if we were going by the number of significant digits and we're not going by the number of significant digits, it looks like we only have 2 here. That's what we're going to do in a minute when we multiply and divide. When we add and subtract, we say, which one of these measurements is least precise? And the answer is clearly this one. This measurement goes to the 10th place. These go out to the 100th. I can't write my final answer to the 100th place because I don't know this first measurement out to the 100th place. I have to use my least precise, so I need to write it to the nearest 10th. Now, there's the 10th place. When you get to this point, you want to round your answer so that it has the correct number of significant digits. 24.36 would correctly round to 24.4 meters. Anytime this digit to the right is 5 or more, you're going to have to round up. If this had been 0.31, we'd have just rounded it to 0.3. Now, generally, when you're working problems, I give you a lot of flexibility on the last digit. I also give you a little flexibility on the number of significant digits. If you should have written it with 3 significant digits and you wrote it to 4, I'm probably okay. If you should have written it with 3 significant digits and you wrote it to 7, I'm probably not okay. All right, anytime you add and subtract, find that least precise, round to that point. Let's do one more. Suppose I have 15,000 meters, 4,200 meters, and 125 meters. I want to add all that up. 15,000 plus 4,200 plus 125 gives me 19,325. But this time, let's look at which is least precise. There's no decimal places, so we have to be a little careful. If we notice, this one, the last known digit is in the thousands place. Remember, these aren't significant. Here, the last known digit is in the hundreds place. Here, the last known digit is in the ones place. 125 is a more precise measurement. They measured it all the way out to the 1. This one, we only have closest to the nearest 1,000. Again, this top one that I wrote is the least precise. Now, that means I need to round to the thousands, just like this is considered to be measured to the thousand. So in terms of significant digits, we should report this answer as 19,000 meters. If I only know this measurement to the thousandths place, it doesn't matter how precisely I know these other two. I cannot write an answer more precise. Okay? So adding and subtracting, we look at precision. All right, so we have a different rule for multiplying and dividing. When multiplying and dividing, the result has the same number of sig figs as the factor with the fewest or the least number of sig figs. Most of the time, we are doing problems that involving multiplying and dividing. This rule is going to be used way more than adding and subtracting. Most of the time, we look at the number of sig figs. So let's suppose that you are calculating this, the area of something. And somebody has measured this out. It's 11.5 centimeters this way. It's 7.5 centimeters wide. And they say, find the area. And you go, I took middle school. Area is length times width. And they go 11.5 times 7.5. And it comes out to be 86.25. Now, interesting thing about units, when you add and subtract, they all have to match. When you multiply and divide, they actually don't. But they work a lot like variables worked when you took Algebra 1. So, centimeters times centimeters, centimeters squared. Okay, if you were in middle school, that's the right answer. In a physics class, that's not the right answer. Let's go back and see. How many sig figs does this one have? You go, well, that's 3. 11.5 is 3. 7.5 is only 2. We need to express our answer to 2 significant digits. So the correct answer in physics, this becomes 86 square centimeters. Now, some of you say, I don't understand why, Ms. Hughes. Well, it's really very simple. That digit is uncertain. That digit is uncertain. When you multiply these two measurements together and they both have a degree of uncertainty, now you have even more uncertainty. We're really not sure about these. You could get a really different answer if this was 11.4 times 7.4 than you get if this is 11.6 times 7.6. There's a broad range. So we go by the least number of significant digits. So correctly, we are going to report this to 86 square centimeters. It seems highly unlikely that if we only know each of these measurements to the 10th of a centimeter, that somehow we could come up with the area and know it all the way out to the 100th. It makes much more sense that if we know them each to the 10th of a centimeter, we can at least be pretty sure we know it to the whole number of square centimeters. So, multiplying and dividing, fewest sig figs. Let's do one more example. Now, if I want to calculate speed, I normally would do distance divided by time. So let's say that I get very precise and I measure my distance to be 23.12 meters. And I measure the time to be 7.04 seconds. I put that in my calculator. 23.12 meters divided by 7.04 seconds. Oh my goodness, here's what my calculator just gave me. 3.284090909. Units, meters divided by seconds, that's a meter per second. Obviously, this is the wrong answer I'm talking about. When you write all of this out, that's way too many significant digits. 23.12 had 4, 7.04 had 3. So based on our rule, we only keep 3 significant digits. So here's 3. I need to look right here. Do I need to round up? No. 4 is not going to round up. So I'm just going to write 3.28 meters per second. Okay. That's my lesson on significant digits. I'm going to do another measurement related video over converting units. So watch this. I hope it helps.